Welcome to another example in our Unsteady heat transfer series. Today we'll delve into a problem involving a spherical object, specifically a copper ball, and how we can determine the convective heat transfer coefficient by observing its temperature change over time. This scenario is common in many thermal engineering applications. Here's the problem. We are measuring the heat transfer coefficient for air flowing at 28 degrees Celsius over a 12.5 millimeter diameter copper sphere. The copper ball has a specific heat capacity of 0.4 kilojoules per kilogram Kelvin and a density rho of 8850 kilograms per meter cubed. Interestingly, the temperature of the ball was measured by two thermocouples, one at the center and one near the surface, both registering the same temperature at any given instant. In a specific test, the initial temperature of the ball was 65 degrees Celsius, and after 1.15 minutes, its temperature dropped by 11 degrees. Our objective is to calculate the heat transfer coefficient for this particular case. Let's begin by outlining the solution. We first list the given parameters and ensure consistent units. The ambient temperature, TA, is 28 degrees Celsius. The radius of the sphere R is half of its diameter, so 12.5 divided by 2 is 6.25 millimeters. We have the specific heat capacity C as 0.4 kilojoules per kilogram Celsius, and the density rho is 8850 kilograms per meter cubed. The initial temperature, TI, is 65 degrees Celsius. Since the temperature decreased by 11 degrees, the final temperature T is 54 degrees Celsius. The time duration tau is 1.15 minutes, which converts to 69 seconds. Our goal is to find the heat transfer coefficient H. Now, to do this, we need to consider the Biot number, Pi, which here is defined as HLC over K, where LC for a sphere is R over 3. The problem states that both thermocouples register the same temperature, implying that the internal thermal resistance is negligible. This allows us to assume that the Biot number is less than 0.1, which validates the use of the lumped capacitance method. Now, under the lumped capacitance assumption, the temperature distribution is given by the equation that is shown on the screen. And this equation can also be written in logarithmic form as shown in the screen. Now, from the logarithmic form of the lumped capacitance, we can rearrange it to directly solve for the heat transfer coefficient H. The equation therefore becomes as shown on the screen, and so for a sphere, the volume to surface ratio ASVC is equals to 3R, and so substituting this, that's how we rewrite that equation. Now, all we need to do is substitute all the known numerical values into this simplified equation. When we do that, and substituting, and then we perform the final multiplication, we find that the heat transfer coefficient H to be approximately equal to 37.71 watts per meter squared Kelvin, and that is our answer. Thanks for watching. If you found this video helpful, please consider subscribing to our channel for more content like this. Don't forget to hit the notification bell so you don't miss out on our latest uploads.